Right, okay, so today we are looking at chemistry, and we are looking at the relative formula mass, the atomic mass, all of that stuff. So we're going to start with the basics. Something that you're going to see on the periodic table. You're going to see elements written in a box like this. So we'll take, I'll go with aluminium, because that's a nice little one that we have. It's got 27 and 13. Those are the two numbers that you're going to see attached to aluminium on the periodic table. Now that smaller number, this is what we call the atomic number. The atomic number is also quite often called the proton number. Reason why we can also call it the proton number is because it literally just counts the number of protons that we have. The protons, kind of a bit of a flashback for people if you haven't seen it before, the protons are the positive charges that we're finding in the middle of the nucleus. So that number is unique to every element. So there's no element that's going to have the same atomic number as any other element. They're all going to have their own unique one. It's basically their ID. So if we want to find the specific element we're looking for, we always look for the atomic number to see what it is. This top number is what we call the relative atomic mass. You will see me shorthanding it later on as RAM. So the relative atomic mass. It's essentially anything that has mass inside in the atom, that's going to add up there, okay? When we look at specifically what makes up that number, that's made from two things: the protons and the neutrons. Okay, so anytime that we have protons and neutrons, they come together to form the mass of that element. The reason why we don't use electrons don't really have that much of a charge, or sorry, not that much of a charge, they don't have that much mass. Okay, so we only count the protons and neutrons because they have a large enough mass to be counted. Electrons technically do have a mass, but it's so small in comparison. If we were to compare, we would say protons have a mass of 1, neutrons have a mass of 1, whereas electrons, they've got a mass of 0.0005, okay? It's tiny. So the mass they have is tiny in comparison to the protons and neutrons, and that's why we don't count it. So that number is your atomic mass, okay? Made up of the protons and neutrons. Now, previously, linking back to other things that we've talked about here in the past, when we look at that atomic mass, we can figure out how many neutrons we have by taking that smaller number away from here. So I'll let you guys try and do the math for me, and I'll check the comment sections in a second. If I wanted to find the number of neutrons, just neutrons, okay, we take the smaller number away. How many neutrons does aluminium have? Where's the best way to put it? Atomic mass. What do we reckon? 14, yeah. Seen loads of people putting it in. So we would just say 27 minus 14, sorry, minus 13 gets us 14. So 27 minus 13 gives us 14, and that right there is the number of neutrons. Okay? So that's just kind of a little recap on stuff we've done before. If we've got like different amounts of neutrons, but it's the same element, we can call those isotopes. Loads of stuff that we're kind of familiar with previously, okay? So you should kind of have that basic bunch of knowledge coming into this. We have every element has a different one of these, different number of protons. We can figure out the neutrons, easy peasy. Key word I want you to remember though is the relative atomic mass. That number up there is what we call the relative atomic mass. Who's giving me stuff? Oh, thank you very much for the roses, much appreciated. So the relative atomic mass is that number at the top, okay? Get familiar with RAM because it's going to change in a second. So that's nice and easy if we have one element like this. But what if we decide we're going to add more elements together? So let's say I wanted to go for something like H2. Okay, so I'm going to put some up in the corner here that we're just going to be using a little bit more in a minute. So we're going to have hydrogen, Hydrogen is 1, 1, and we're going to have oxygen, which is 16, 8. Okay, those are two elements. If you look at your periodic table, that's what you're going to end up seeing up there for both. Okay, so let's say I've got H2. Okay, well this isn't matching up with what I have here. I don't have H2. I do have a H, but I don't have two of them. So if I see H2, what that really means is 2 times that. That's what I'm doing. I've got 2 times those. God, I've got loads of people handing in roses. I really appreciate that. Thank you. So that just means I've got 2 of these. And again, I'm multiplying it by this top number. So that just means 2 times 1 is equal to 2. Okay, that's what it equals. So H2, its mass is going to be 2. This, though, is not what we call the relative atomic mass anymore. We call this the relative formula mass. Okay, because it's not an element anymore. This is for, well, it's not for one single atom anymore. This is for one atom. This is for more than one. So if I'm dealing with a singular one, I'll call it the relative atomic mass. If I'm dealing with more than one atom, we're going to be calling it, or if it's changed into a molecule, so we can call that a molecule, we can call that the relative formula mass. Quite often you'll see it shorthanded as the RFM. Okay? God, thank you very much, Liam. Really appreciate it. So, relative formula mass, that's where this number comes from. Okay? So, let's keep going on that line. We saw that H2 is equal to 2. Let's say we've got O2, and this is one for you to try. We said H2, sorry now, I'm going to put it over here, make it easier, is 2 times 1. Let's say we are adding it to oxygen, okay, but oxygen like this. Can we try to figure out what the relative formula mass for O2 might be? Bear in mind, we've got 16 and 8 here. Have a go, try and figure out what the relative formula mass for me in the comment section is for O2. Love it. Seeing some people, oh, we've got a couple of people that are probably slightly wrong with it. So remember, relative atomic mass, we're taking the top numbers. Top numbers always for this one. Someone said, I feel productive watching this live. You should. You should. Good. Right, we're going to go with it again. So, remember, we start by taking the mass numbers up here. So we're dealing with these numbers, not the smaller ones. Those are for the protons only. So we're going to say we've got 2 of them. We are looking at oxygen. Oxygen is 16. So 2 times 16 is equal to 32. Now when we're talking about 32 and 2, what we're actually talking about is if we were to put them in masses, one molecule of O2 would be 32 grams. One molecule of H2 would be 2 grams. So we're actually looking at masses, if we're trying to physically put a mass on these molecules. So H2 and O2, they're looking at 2 grams, 32 grams. Right, let's say we now want to have a chemical reaction. So we want to have a situation where we're reacting that hydrogen with the oxygen, and you can try and make a prediction for me of how much the mass would be for H2O. So 1 second now, let's tidy this up. I'll give you the balanced version of this. For the eagle-eyed amongst you, you'll notice we only have 1 oxygen here. We've got 2 oxygens here. So if we want to balance it, we have to put a 2 outside of this so that we have 2 oxygens, but that means we have 4 hydrogens. So this would actually be your balanced equation. Okay? Same rule as what we were doing a while ago though for the molecules, but count it as like a little bracket. Count it as a little bracket, so you've got to do H2 and O2. Can we figure out how many grams we're going to be dealing with on both sides? Okay, we'll start with this. We've got 2 moles of H2. So we're going to put 2 outside this bracket. What's going to be going on inside the bracket? What am I multiplying inside this bracket for the H2? Damn, I remember doing this in 8th grade. Yeah, we're back doing some of the basic math stuff for chemistry here. Yeah, we've got 2 times 1, because the mass of hydrogen is 1, which is equal to 2. So it's 2 times 2. What's the easiest way? I should do it over here. So 2 times 2. Close my bracket a bit easier. And oxygen, we said a while ago, was the same as saying 16 times 2. So that's 32. And then over here, we've got 2 moles of H2O. 2 H's, that's going to be 2 times 1. Plus the 16 from the oxygen. So that's going to be 18. Okay, so 2 times 18, and that's going to give us 36. Okay, now if we look at the left hand side and the right hand side, 2 times 2 is going to be 4, plus 32. If we add those together, that's also 36. This is what we call the conservation of mass. So we're going to be looking at whatever we had on the left hand side in terms of its mass is going to be present somewhere on the right hand side as well. So the saying there, like I was saying, this is called a conservation of mass. The amount we have on the left has to be present somewhere on the right. It can't just disappear into nowhere. If it does, there's probably something slightly wrong, or it's a case of we're actually not looking at it right. We might have a gas that's leaking somewhere and you're losing it, like a product as a gas. Quite often, if you think about water, water is present as a liquid but can be present as a gas. These two that we have here, they are gases, so we might be losing them somewhere along the way. There's a whole pile of different things. Questions though, questions. What about balancing them? I have it balanced. Everything is balanced. We've got 36 grams and 36 grams. That's a way that we can prove that this equation is balanced. If we're looking at it in terms of the molecules and the atoms that are present on both sides, we've got 4 hydrogen atoms. We've got 2 oxygens, 4 hydrogens, 2 oxygens. It's balanced. That's how we know. Boy, what? Balanced. It is balanced. Oh, and someone asked me, will I ever go over reduction oxidation? Yeah, that's my plan. I'm not a million miles off of it. I will be doing that very, very soon. Someone said, ooh, do you have videos in one place where I can rewatch? Yeah, they're all on my YouTube. Go click on it and I'll actually be putting up all my live lessons really soon there. Probably after this. After this, I will probably upload one full one. So you'll have some old ones to go up onto as well. The gas laws, I will further down the line. Don't worry, they're all going to be there. Do you do other classes? Well, I could do classes in school, but at the moment, this is kind of the ones I do. I do some tutoring on the side as well, but like mostly I'm like in school and I'll do a couple of lessons here. I am going to do a physics one as well tomorrow, so you'll get that as well. Please teach me visual neuroscience. Do me a favor. Actually, can I do anything for that? Probably not. I don't think it comes up anywhere, but since we're on that point though, if anyone does have questions, ask me over my Instagram. I put a question box up on my story specifically for you to ask your questions if I'm not answering them in the live today. So yeah, go there. Right, should we just drive on with this? So going back to it again, we had 2 moles of H2 reacting with 1 mole of O2 and it creates 2 moles of H2O. Now I'm using this word mole a lot, and a lot of you are probably like, why are you bringing an animal into it? You're dead right. It's a bit of a funny one, but a mole is just a term that we have that's used for a measurement. So I'll explain that a little bit more. So moles. Now I have done a TikTok on moles before, but I'm guessing most of you haven't seen it. If you have, let me know in the comment section if you've seen the TikTok I made about moles. Moles is just a unit of measurement, okay? So moles can be looked at in a couple of different ways. 1 mole is like saying 1 relative formula mass of the substance. You could also say 1 mole is like having 6.02 by 10 to the 23 atoms or molecules of a substance. Okay, now that's still probably not clearing things up for a lot of people here. So let's simplify it. But what do we mean about that? So 1 mole equaling this amount of atoms is like when you have 1 mile. Actually, we won't go 1 mile. We'll go 1 kilometer because it's easier units to see. If we had 1 kilometer, well, if we were converting that to meters, that's like saying we've got 1,000 meters. Well, if we were converting that to centimeters or whatever it is, we could keep getting smaller and smaller. Atoms and molecules just happen to be the smallest part that we have making up any kind of substance that we're dealing with. So they're really, really, really small. Like if I asked you to get 1 single atom of carbon or hydrogen or whatever, you'd be kind of going, come here, that's tiny. Like I can't get 1 atom of it. And I go, well, okay, let's try and find an amount that we can use that would be like relatively big enough for us to actually manage. And that's where this came along. We said, well, if we get this many atoms, which is a lot. I know it looks small right now, but 6.02 by 10 to the 23 is 602 and 21 more zeros afterwards. Like it's a lot. It's a lot of atoms. So we just get that many and say, okay, if we have that many atoms of H or of O or whatever we're dealing with, that's going to be worth 1 mole. 1 mole is just the word that we use as a unit of measurement. Some scientists, Avogadro in particular, when we look at him, Avogadro is the scientist that said, this is what we're going to name it, tough luck. It's like who decided to name things miles or kilometers or pascals or pressure, all of that stuff. When we look at different units, a mole is just a unit of measurement. That's all it is. But the way it's linked for us is if we're talking about 1 mole, that's also saying that it's equivalent to 1 of the relative formula masses of a substance. Okay, it's the exact same thing. So if we've got the entire relative formula mass of a substance, we can say that that's the equivalent of 1 mole. Now that's going to become very useful in a minute when we have different substances that don't fully add up to the relative formula mass. I'll explain that a little bit more in a second. So if I have something like, we'll keep it basic, we'll say H2, right? We'll go back to our H2 because that's what we were using. If I have 6.02 by 10 to the 23 molecules of H2, we can call that 1 mole of H2. If I have got 2 grams, because we worked it out a while ago, we said 2 times 1 is equal to 2, so 2 grams. If I've got 2 grams of hydrogen gas, we can call that the relative formula mass of H2. Those are the exact same thing. It's the same thing. Okay, I know we overcomplicate it, we make it sound really difficult, but they're exactly the same thing. The relative formula mass is the same as 1 mole. We're just giving it a different name. It's just a different unit. Any questions so far? My relative is useless. I'm in 2 maths classes right now. What? Does this man think I go on TikTok to pay attention to more numbers than she? Alex? No. But you're more than welcome to go somewhere else. I don't really care. Do you, my friend? Don't care. Short hair, don't care. I don't get it. Okay, so right. Imagine that you have got, oh, what's the easiest way? Right, let's say it's like you and 4 of your friends. Okay, so there's 5 of you in total, right? If you nicknamed your group, it's like, you know how we all have a WhatsApp group, right? Every group of friends has a WhatsApp group. Whatever your WhatsApp group is, that is one WhatsApp group of your friends. Okay, it's made up of however many of you there are. Okay, now if we take the equivalent there, we might say, well, 1 mole of your WhatsApp group, named whatever it is, has got 5 of you in it. Okay, so it takes the 5 of you to make 1 mole. If there's not all 5 of you there, it's not 1 mole of that group of friends of yours. So like it's just a unit of measurement. Now if we put all of you on a scale, you're going to be able to get a mass for your group, right? Let's say, God, we'll take the average. Let's say if like everyone was on average 70 kgs. I know you're not, but look, we'll just say an average. So we'll say your group weighs a mass of 350 kilograms, okay? So if we don't have 350 kilograms of you, let's say one person isn't there that day, then you're going to go, well, we don't have the full WhatsApp group present. We're all not there. Someone is missing from the group, so we are not 1 mole of our WhatsApp group. There's something missing. So then you can work out a percentage of how much of you is there. You can go, well, we've got 300 of the 350. So that's what? That's 85 percent of it is there, or 0.85 of a mole of our WhatsApp group is present. Like, it's just about how many of you are there. So when we're looking at a mole, we're saying that there are this many atoms present to get 1 mole. If we don't have all of those atoms, we don't have 1 mole. If we don't have all of this mass, we don't have 1 mole, because the relative formula mass is still equal to 1 mole. Okay, it'll make more sense when we do something in a second, right? So if we were to take that H2, right, and we know the relative formula mass for H2 is equal to 2 grams. Well, let's say I don't have 2 grams of hydrogen gas. Let's say I've only got 1 gram. Well, I'm going to say 1 gram, because that's the amount we have, over 2 grams will be however amount of moles, the amount of mole I do have. Okay, so this is what we say. We say with the amount I have divided by the relative formula mass. In this case, I've got 1 gram. If I divide it by 2, I've got 0.5 moles. That's all we're doing. We're just taking the amount that I do have and dividing it by the relative formula mass over and over again. Okay? He gives it what? Do you understand grades this year in science? Depends on the country. Any other questions so far? Because I know that's going to be, yeah, there's going to be a lot of whats. What is the topic? We're looking at moles, relative formula mass. I'm going to probably go back to relative formula mass because I feel like I've confused a few people. I'd rather do this than school. Most people would, if I'm perfectly honest. Am I late, please? You are late, but it's like not going to massively affect it. A-level topics. I probably won't do them for a while, and to be honest, what I will do is I'll probably do that separately on a separate thing. So I might even go as far as setting up Zooms. I'm not sure. What do we need to count RFM? So what you need for the RFM is you're going to need your periodic table. So if you've got a periodic table, you can figure out the different numbers. I'll tell you what, let's go back and focus on the relative formula mass, because I think it confused people when I started going into the moles a little bit. So let's go right back to the relative formula mass part, because I think we could do a bit of practice there anyway. So I've got a couple of them lined out already. Things that we're going to need to know in advance. We are going to need hydrogen again. I've made that box too big because I need to fit 4 of them across here. Okay, hydrogen is 1,1. Carbon is 12,6. Nitrogen is 14,7. And oxygen is 16,8. Okay, so those are the 4 that we're going to be focusing on today. So we'll do some practice. Can we calculate the relative formula mass Okay, that means that we're going to be using these top numbers anytime that we see one of these elements for the following. Most of you will have done these already. So you'll have done hydrogen, H2. You'll have done oxygen, O2. You might not have done this one, H2O. You might also not have done this one, C6H12O6. And we'll throw in one just for fun. Yeah, let's do the other one. We will do C9H8O4. Okay, this is aspirin. So we're going to have a go at working these out. Now what I'll do is, for the people who've been here since the start and you find it easy, you can jump down to these two because you're probably looking at the more difficult stuff there anyway. If you haven't done this before or you're like, what's going on, and you're new to it, I'll work through these three while everyone else works on those two. So those two are harder. I'll put it up here so you can see it a bit better. C9H8O4. Okay, have a go at figuring that one out. And then we had the C6H12O6. Okay, I would recommend using your calculator. You're going to be allowed to have them on the day, so you might as well. So that's what we're working out. So we'll start, for anyone who isn't used to this or you want to get better at it, let's start with H2. So H, we can see up here, is the number 1. So we're just going to say 1. The amount we have is 2. Okay, so this is the relative atomic mass, and we're multiplying by the amount of atoms of it. That equals 2. Easy peasy. We're going to do the same now for oxygen. Oxygen, we have the relative atomic mass is 16. The amount that we have is 2. So 16 times 2 is 32. Okay, we should say grams. H2O a little bit more difficult now because we have two different elements. We have got hydrogen, which is H, which is 1 by 2, plus we have oxygen, which is 16. So 16 plus 2 is going to be 18. Okay, so all we're doing is we're taking the relative atomic mass, those big numbers, and we're multiplying it by the amount of the atoms present. I'll double check if everyone's okay with those, but if you are okay, have a go at these ones quickly. I'll be back over. Someone's like 34. What are we 34ing? It should be 18 plus 2. 69. Oh, a little bit off with 69 there. Enthalpy and entropy, do me a favor, ask that question over my Instagram story because I have a little box open for you guys for those questions so I can give you loads more details. Aoife, thank you very much. I can do this all day. I love it. Like, this is, if people can do it, great, fantastic. I love these videos. Oh, glad you're finding them useful. What's the purpose of searching for the relative formula mass? Well, I'll show you in a second because it's quite useful to break them down and identify. Like if you were, do you know what, it's best when I get to aspirin, it'll make a lot more sense when I start doing it. So we'll go and jump to glucose first because I quite like glucose. So if we start with glucose, we have C6H12O6. So that means I've got 6 carbons, 12 hydrogens, 6 oxygens. So we go down, we do our little brackets again. Carbon we see is 12. Ooh, we have 6 of them, so we multiply it by 6. Plus hydrogen is 1. We multiply it by the 12. And then oxygen is 16. We multiply it by the 6. Okay, that's what we're doing. We're just going here and here. Okay, so when we work out the relative formula mass, that's what we're going to end up with. So 12 times 6 is... 12 times 6, this is numbers that I should be doing in my head, but I would rather be safe than sorry. 12 times 6 is 72, plus 1 times 12 is 12, plus, I think this should be 96. Oh, 96, there we go. So that's what those three numbers equal. We add them all together and that should come out at 180. Boom. So all of those together is equal to 180 grams. So 1 mole of glucose is going to weigh 180 grams. So 1 mole That's the equivalent of C6H12O6. Okay, all we're doing is we're taking the amount of each of those atoms and we're multiplying them to add them all together. Okay, it's just taking the mass of all the individual pieces and putting them together. Oh, someone said a good question. So the value of each letter corresponds to the number in the upper left. Yeah, so you're looking at the bigger numbers, because I know for some reason, we just can't seem to do it across the globe, where we just go, the big number should be on the top, the smaller number should be at the bottom. Some countries reverse it and they put the smaller number on top, and I'm like, why would you do that? You're just making life more difficult. But the bigger number is always the one we're using for the relative atomic mass. Okay? Will these be in the leaving cert? Yeah, you do need this for leaving cert chemistry. Is 1 gram equal to 1 RFM? No. So grams is what we measure the RFM in, but every different substance or molecule or whatever you're dealing with will have a different amount of grams, but it's just that it's one of the relative formula mass for that substance. Okay, so 1 gram might not be the RFM. The RFM is a collection of all the different masses together. I've seen. Okay, I'm lost on whatever question was asked by David Brady. Sorry. Any questions? Any other questions? RFM is equal to grams per mole. Yes, yeah. Space I won't have for another while. Just live helping out, not an actual school, don't worry. Please do some redox equations. If I've got time at the end, I will. I have a question. Ask me. What class is this? This is mostly for chemistry. How many grams are in 1 mole? It depends on the substance. So every substance would have a different amount of grams. So in this scenario, I've got, this is glucose, I should say that somewhere. This is glucose. So 1 mole of glucose has got 180 grams. But a while ago, we saw that 1 mole of hydrogen, H2, well, 1 mole of that was 2 grams. That's 1 mole. The mole is just a name that we give for a set amount of atoms, okay? So in this scenario, where we have 1 mole, it means that we've got 6.02 by 10 to the 23 molecules of hydrogen, or, in this case, of molecules of glucose. So the mole is just a term that we give to it when we have that amount of atoms or molecules. That's all a mole is. It's just a set amount of them. So it's like another way to think about it, right? There's 1 of me, okay, and I know my mass. So 1 Tygo Donovan is going to have a mass of 92 kgs, whatever it is. Your mass is going to be different. Whatever your mass is, if you stood on the scale, you go, well, 1 of me is equal to whatever your mass is. But the amount of us there is still the same. There's only 1 of me, there's only 1 of you. So we're looking at 2 different masses, but in terms of like humans, it's 1 human of me, 1 human of you. 1 mole is just a term that we're giving to an amount of atoms. That's all it is. Moles is just a unit we give to a set amount of atoms. But atoms have different masses, just like humans have different masses, so they all weigh differently. Who's in the class? Someone's like, if y'all need a lot of help with redox. Who's Sabina? No idea. Is Sabina, who is Sabina, if you're here, congratulations for being here. Sir, are you only going to teach calculations, or do we tackle topics that aren't associated with number? What do you mean? Give me more details, I don't quite get you. Do I prefer physics chem? Can I have a quick recap? So what I've done so far is we talked about relative atomic mass. So we're saying that these bigger numbers that you see on each of the elements, they're called relative atomic masses. But if you have a molecule that's made up of different atoms from different elements, you have to add them all together. So in this scenario, I had something like glucose, which has got 6 carbons, 12 hydrogens, and 6 oxygens. So we take the relative atomic mass for each, and we multiply it by the amount of them that are there. That's all we're doing. And that gives you a set amount of grams. We call that the relative formula mass. And we said that one of the relative formula mass is still the equivalent of 1 mole. Okay? That's all we've done so far. Right, let's do the next one. So we'll get rid of glucose a second. Sorry if anyone needed it. So we have C9H8O4. Same scenario as last time. All we're going to do is we're going to take the amount of carbons. We're going to multiply them by the relative atomic mass, which is 12. Then we do the same for hydrogen. We have other way around. 1 times 8. And then oxygen, we have got 16 times 4. Have a go, quickly tot them up. I think I've got my number already done out. Can we figure out how much is the relative formula mass for aspirin? Have a go quickly. What do we think? What does it work out at? Can I go to the bathroom? Yeah, go for it. 200. Is it 200? I don't think it is. 180. That sounds about right. If a mole represents an absolute number value of atoms and the relative atomic mass is weight, how do they end up equal? So a couple of things. So a mole representing an absolute number of value, yes, you're talking about, sorry, I just realized I'm in the way for this. You're talking about the amount of atoms or molecules present. Relative atomic mass are just those ones up here. So there's a difference between relative atomic mass and relative formula mass. Relative atomic mass is just the number that we have for each of these individual elements. So technically, if you had just hydrogen, yes, that number, the relative atomic mass, you're technically talking about 6.02 by 10 to the 23 atoms. But the problem you have is that H doesn't exist by itself in nature. It exists as H2. So you have to look at it as molecules then. And then it gets a little bit more confusing because you're not dealing with 6.02 by 10 to 23 atoms. You're dealing with 6.02 by 10 to 23 molecules because the hydrogens have to bond together. Slightly different, and that's why we call that the relative formula mass. It would be great if all the elements were like all individual, where you only have one atom of this or one atom of that, but because they stick together and you end up situations where they all bond like this, we have to have a different way of measuring them. So let's go with it. So 12 times 9 is equal to 108, plus 1 times 8 is 8, and 16 times 4 is 64. 64 plus 8 plus 108 is equal to 180. Okay, now we came up across glucose a while ago, and we said glucose, C6H12O6, that was also worth 180 grams. So we've got two different substances that have got the exact same relative formula mass. Okay, so they've got the same mass. Technically, there's the same number of molecules, but their makeup is different. This one has got 9 carbons and 8 hydrogens, 4 oxygens. This one's got 6 carbons, 12 hydrogens, and 6 oxygens. So we can have different substances equaling the same amount in terms of their mass. What's different is how they are set up to be that mass. It's just slightly different, okay? This is still technically the relative formula mass of aspirin. That's still technically the relative formula mass of glucose. It's 1 mole of each, okay? But if we're thinking about what we use them for in real life, you could probably, not that I'm recommending you should, I wouldn't recommend it, but you could have 180 grams of sugar in your day and you'd be fine. If you had 180 grams of aspirin in the day, you're probably going to end up shutting down your liver and having to go into the doctors. It is really dangerous. So while we can work out the grams that you might have for a mole of stuff, it doesn't recommend that you should have that much. It's dangerous. And that's where looking at volumes of stuff that you're making becomes really, really important. Maybe if you're working in a pharmaceutical company, you might end up making 180 grams of aspirin. Doesn't mean you're taking it. It means you're making it. And someone asked earlier, why would it be important for us to know what a mole is and why we do all this? It's for chemical companies. Where I'm from in Ireland, there are 7 or 8 different pharmaceutical companies just down the road from me where they're all making different products they have to have chemical equations like this where they're making different things. It's really, really fundamentally important for what's going on. Okay, let's have a little bit of fun. I won't say fun with it, but let's play around with another formula that you guys are probably used to seeing. Let's talk about respiration. Okay, so you're probably used to seeing respiration as glucose, which is C6H12O6, plus oxygen, which is O2. When we respire, we're going to end up making CO2 and H2O. Okay, first thing you should do is technically balance this. I'm going to do it really quickly for you because it's one of those ones where you just need to like remember the numbers. But you could shortcut it to 6O2, 6CO2 and 6H2O, the devil's number. Okay, so this is the formula for respiration. Let's go about working out how much mass is actually involved in respiration here. So again, we have this already. We worked out that this was 12 times 6 plus 1 times 12 plus 16 times 6. We did that earlier, so I'm just going to shorthand it always. That was equal to 180 grams. 602 though, 602, we put the 6 outside the bracket. We have O2 being 16 and times 2. So I'm going to leave this one to you to work out, but it's 6 times 32. Have a go cracking that up. And then over here, we haven't done CO2 yet, so it's 6 times, what's carbon? That's 12 plus 16 times 2. And we have 6 times 1 times 2 plus 16. Okay, all of that together. I bet you when we look at the left hand side versus the right hand side, the mass we get on the left will be the same as the mass we have on the right. Oh, you are doing mass and stuff. Yup. So have a go. I've done most of the work for you. I came from the FYP. Oh, thanks for coming from the FYP. Hope you're kind of going, oh yeah. Sir, can you do balancing equations? Yeah, I might do a little bit afterwards. Earlier you said the bottom number is always different. Is that the same for the top number? Not necessarily. So the top number technically could be the same. The problem you have is that that's what we call isotopes. I'll give you an example in a second. Someone's like, is this a maths lesson? It's not. Do you enjoy this? I do, I suppose. Otherwise I wouldn't be doing it. Oh, someone's asked a really good question. I'm going to write that down because I'm going to come back to it in a second because that's one we could all do. What mass of iron is contained in 86.6 grams of calciferite? CuFeS2. Okay, bear with me. I'm going to write that one down. What was it? 86.6 grams of CuFe. Was it S2? Did I see S2? Okay, good. Okay, right. We'll come back to that one in a second. I like that question. That's going to be a tough one for a lot of people. What grade is this? We're probably looking, if like in terms of age, it's probably easier to go with age because I know a lot of people from different countries for this. In terms of age, it's probably like if you're 15, 16, 17. Do I have a mic on? I do. I'm trying to get a mic going so that at least I can put this on YouTube afterwards. Right, let's have a go at this. So, I've done the glucose for you already. So 6 times 32 is equal to 192. Wrong colour. So, if we take the 192 and we add it to the 180 grams, on the left-hand side, we have got 372 grams in this left-hand side. So at the start of our reaction, we have got 372 grams. Let's go to the right-hand side. So 16 times 2, we know that is going to be 32. 32 plus 12 is going to be 44. Okay. 44 times 6 is 264. Plus, we've got 1 times 2 is going to be 2. 2 plus 16 is 18. 18 times 6 is 108. 108 plus 264 is going to be 372. Balanced. So we know that we have the same amount on the left and on the right. Okay, so that's how we know we've conserved everything. It's how you can check if you've got the balancing of the equation correct as well. Now, someone asked a really good question here. If I have 86.6 grams of CuFeS2, can't remember what the full name of it was, how much of that was it iron? Was it iron they were asking about? So let's figure out. So, very good question. I like this question. So, from the period, I'm going to have to take my periodic table in a second for this. So, CuFeS2. We're going to need 3 different, bear with me, let me get out a table. Oh, I didn't even get around to paracetamol yet. So we had copper. Copper is Cu 63.5, 29. There we go. Iron Fe is 56 and 26. And sulfur is 32, isn't it? Yeah, 32 and 16. Okay, so the numbers that we're going to be using are going to be these ones on top. The 63.5, 56 and 32. Okay, so the first job that we have is that we need to figure out, okay, what is the relative formula mass of CuFeS2. So same as what we were doing earlier, we take Cu, we have one of them, and we're multiplying it by 63.5. So 63.5 times 1, that's fine, plus iron. Iron is 56. We have one of them, so it's times 1. And then S, we have 32 times 2, because we have 2 of them. So this whole thing together, let's calculate it out. 63.5 plus 56 plus 32 times 2 is going to be 64. Plus 64. So in total, we have got 183.5 grams. Okay, so that's the relative formula mass of CuFeS2. Okay, take that in mind with it at the moment. So if we had a full amount of this, it would be equal to 183.5 grams. But we don't have a full amount of that. We have 86.6. So we're not up to the full amount. We're not at 1 mole. So we need to figure out how much of a mole we do have of that. So the easiest way of working that out we would look at, sorry now, I'm just having a bit of a moment where am I complicating this more than I need to? So we're going to get rid of that a second. Now we're going to do 2 things with this. So of that 183.5, we can do one first off. We're going to say iron of this is going to be 56 grams. So 56 grams of that 183.5 is going to be iron. So we can say iron makes up 56 divided by 183.5. So 56 divided by 183.5, that tells me that iron, Fe, makes up 0.305 of the whole mole, or we could say even 30.5% of this. Okay, that's what iron makes up. Okay, which means of the 86.6, Fe, the iron, makes up 30.5% of the 86.6. So we just go 86.6 times 30.5%. Where's the percentage sign when I need it? Oh my god, I can't even see it. It's so blind. Just going to go 0.305. Which means that iron of this, 26.4 grams of iron. Okay, I know I've kind of gone around it in a bit of a funny way for you, but that's Kong died. What? But yeah, that is the answer that you were looking for there a second ago. So you had 86.6 grams, but actually the moles that we have is this. Iron makes up 30.5 grams of it. So we just go off and we find out that 30.5% of 86.6 is 26.4. Hope that makes sense. Any other questions? Actually, since we're on that, I'm at that point now where I'm a little bit free to do whatever. Can I teach you ions? I'll do ions. Can you screenshot? Yeah, go for it. Screenshot. Ions. I'll do ions in a second. This is better than Zoom. Well, at least with Zoom I'd be able to go off and actually like put up slides as well. Right, someone asked about ions. I'll do ions quickly. Because ions is nice and simple, to be fair. Before I do it though, if anyone has any other questions, feel free to ask them to me over my... There we go. Feel free to ask them over on my Instagram. I've got a question thing up on my story, so you can ask me there as well, because I won't get around to everyone's questions. Right, ions is pretty straightforward, so we'll take something like sodium, Na. Actually, do I want to move it over to the left a little piece? So, sodium, Na, got 2 in the first shell, 8 in the second, and 1 in the third. I'm not going to lie, I'm pretty happy with that. So this is what a sodium atom traditionally looks like. Now, if this electron goes off somewhere, okay, I'm going to just write that as 1e, disappears, then this electron has disappeared from the outer shell, happens quite regularly, and now this sodium has lost something that's negative. Now, I always say atoms are like friendship groups, because you're going to have positive people, you're going to have negative people, you're going to have neutral people. If your friendship group loses someone, then your friendship group becomes positive. So this atom has lost something that was negative. Because it's lost something negative, it becomes positive. +1. Okay? Easiest way to think about it. So you lose something negative, you become positive. We call that a cation. Cations. Oh my god. Okay, they're positive ions. I'll give you a cringy way of remembering that in a second. Now, let's take another one. Let's say we'll go with chlorine. So chlorine has got 2 electrons in the first shell, 8 electrons in the second, and it's got 7 in the third. 1, 2, 3, 4, 5, 6, and 7. Okay, so for chlorine, it's actually easier to gain 1 electron than to lose 7. So let's say that that electron here actually comes in. Okay, so it's gone in there. Now, in this scenario, it's like your friendship group has gained something that's negative. So you've gained a negative person, which makes the entire group more negative. So in this scenario, chlorine becomes negative. We call those anions. They're negative. I've heard people remember anions by saying it sounds like onions, and onions make you cry, which makes you feel bad, which means that they're negative. Anions are negative. Personally, I just remember anions as the opposite of cations, and I'll go with how I remember cations. This is the cringiest way ever, but you're going to laugh and you'll remember it. The way I remember cations, and that they're positive, cats have got paws, so they are positive. You may now die internally inside like I am dying. But the other one, you can remember it as, The alternative name for a cat is and they are a positive ion. So cats are pussies, positive. Even more, I've died inside. Literally, this is why I'm single, making terrible jokes like that. But yes, cat ions, they're positive or they're positive, and then anions are just the opposite, so they're negative. Okay, any other questions? I know that's the anions one sorted now. Any other questions? I hate that. I use that all the time as well because it's the easiest way. Something positive and draws in the cat. Yeah, it's just the easiest way of remembering it. And I cringe every time I say it, but it's easy to remember. When do you normally do lives? So normally I do them on Wednesdays at this time. So I have done my chemistry today. I'll actually be ending probably soon enough. Tomorrow I'm going to do physics as a bonus. I normally only do one a week, but I figured I've spent the entire hour now doing chemistry, so I'll do physics tomorrow just as a bonus, and then next week I will do biology. Oh my god, how much? Oh my god, right, do me a favor, ask me that question over on my Instagram story because I'll need a lot more time than just what I'm doing. Can I screenshot? Yeah, go for it. Okay, I'm seeing loads of good questions coming in. Alkanes, alkenes, all that stuff. Do me a favor, go over to my Instagram and ask them in my story. Okay, so I put a little box there for your questions. Ask me there. Hit the follow button while you're there as well. Why not? And I will answer all of them over the next 24 hours. What was the analogy for the anion? Anions, they look a bit like the spelling for onion, and onion make you cry, so they're negative. Anions are negative. Okay, that's the way that some people remember it. I personally don't like that one. Thank you, anytime, Jason. But yeah, ask your questions over there. Head over to my YouTube channel as well. I'm going to be uploading all of these live lessons over there as well, so that you get a chance to, like, if you want to review it, it's all there. I try and break some of them down into smaller pieces, so you'll get there as well. 2 + 2 is 4. But yeah, it's all over my Instagram and my YouTube. Just go check them out. Effie is Iron Man. Yeah, Iron Man is technically a woman. There you go. It's female. Any other questions? Any other questions quickly before I go? Thank you for the lesson. Anytime.